Oh, I'm sorry. I didn't see that. Let me just. Uh, okay. Um. Yeah, that's better. Hello, everyone. My name is Aaron Meyer, and I am a researcher with the Carbon Sequestration and Engineering Research Group here at the University of Utah, under the direction of Dr. Brian McPherson. If you're watching this video, you must at least be feigning interest in the field of carbon capture, storage, and detection. But if by chance you're not feigning interest and are truly intrigued by this field, then hello, and welcome to your next bingeable video series, Carbon Dioxide and Methane's Surface Source Location and Gaseous Mass Flux Quantification. Sounds like something you could curl up on the couch with a big bowl of popcorn and a hot chocolate, right? Let's get started. I'd like to begin by describing the structure of this video series. The video you are watching now is a general project overview, giving some background into the field of carbon sequestration and diving a bit deeper into the goals of our surface monitoring project. Accompanying this overview are 3 technically detailed videos describing the procedures, methods, settings, data explanations, and mathematical concepts of 3 subsections of this project, including an equipment-specific video, a video detailing the inner workings of the live data stream, and the details of the bench scale experiments. Let's start by taking a look into the field of geologic carbon sequestration, as a bit of background is necessary to understand the overall goal of the project. Typically, when fossil fuels are burned to create energy, the carbon dioxide byproduct of this process is emitted into the atmosphere, whereas properties as a greenhouse gas contribute to global climate change. However, with new techniques, this carbon byproduct can be captured as opposed to emitted into the atmosphere. This captured carbon is then pressurized and piped to a dedicated sequestration field. Using injection wells, the carbon dioxide is deposited into deep underground rock formations. Sequestering, or trapping the carbon deep underground, is a method for preventing its release into the atmosphere. Due to the relatively new nature of this process, diligent simulation, risk assessment, and monitoring are necessary to ensure that the sequestered carbon is remaining trapped underground. This is where my research comes into the picture. We wish to ensure that the carbon is staying underground, and one method for assessing this goal is to monitor carbon dioxide levels on the surface above a sequestration field. Suppose an old wellbore is allowing some of the trapped carbon to make its way to the surface. Theoretically, a large enough leak should be detectable in elevated surface CO2 levels. Leaks may exist as carbon makes its way up and out old wellbores, unidentified faults, or other unknown reasons. By using equipment detecting carbon concentrations in the air, and by monitoring air movement above carbon sequestration fields, we hope to be able to detect, locate, and quantify any leaks from the sequestration field. As evidenced in this thesis statement, the problem we hope to address breaks down into 3 specific sections, each building on the previous. First, we must be able to detect a substantial carbon leak. How do we assess whether elevated levels of carbon are coming from a storage site leak as opposed to an external source? Next, we must be able to locate the site of the carbon leak. Once we are confident that we are indeed detecting a point source of CO2 emission, can we accurately predict where the leak is coming from? Finally, we hope to be able to quantify the leaks in terms of a mass flux in grams per second or a similar unit of measure. This step is by far the most difficult and has become the current area of my specific study. Additionally, due to the nature of the large amount of data required for analysis, as well as the recent push for immediate data access, creating a system that can do the above analyses while being able to, quote, live stream the data as nearly as possible is a major part of the project. A web-based dashboard allowing an operator to immediately see a potential leak and assess the situation is highly desirable. The equipment used in this project consists of a variety of concentration measurement devices, including the Picaro G2311F cavity ring down spectrometer and Licor's 8100A continuous measurement carbon dioxide detection device. Additionally, because we hope to quantify air movement above a sequestration field, we utilized Applied Technology's 3D sonic anemometer measuring 3-directional wind data at a 10 Hz data rate. Also, we utilize Kestrel's 4000 weather meter, a simple windmill anemometer, and the Vantage Pro 2 weather station, which is a cup anemometer that allows us to remotely record data using the Davis Envoy 8X data receiver. Additional technical specifications, procedures, and issues with the equipment that we encountered along the way can be found in the accompanying equipment video of this video series. In order to develop the techniques, algorithms, and ideas necessary to accomplish these objectives, controlled experiments were conducted. We first examined the detect portion of the project. Using a known source with a high mass flux of carbon dioxide, we can assess the equipment's ability to see an elevated level of CO2. To simulate a field leak of CO2, we utilize a restaurant exhaust vent on the roof of the student union. The vent resides at the end of a ducting system originating with the hoods above 2 stoves and 2 deep fryers in the Panda Express of the Union. The stoves are burning natural gas and therefore releasing methane and CO2 from the vent on the roof. We first set up a monitoring station using the Lycor 8100 directly at the vent output. The detection tower using the Picaro spectrometer and 3D anemometer is then set up some distance away from the vent. Using these data, we were able to confirm that we were in fact detecting the fluctuation in emissions from the vent. This animation is a representation of the experiment. The top plot shows a measured concentration of CO2 being emitted from the vent, and the bottom shows the concentration of CO2 being detected from some distance away. If we play this in time, we can see the clear correlation between the two across multiple experiments confirms the fact that the elevated levels of CO2 seen at the monitoring tower are in fact the tower detecting the large source of CO2, the vent. The next task to tackle was locating what direction the identified source was coming from. Again, the Panda Express vent was used for study in the same type of experiments. The eddy flux tower, consisting of the Picaro CO2 detection equipment and the 3D anemometer, was set up at a distance from the vent, and the Lycor CO2 analyzer was set up at the vent exit. Using the data visualization app developed in R-Shiny, the code for which an explanation can be found in the streaming video and accompanying folders, we find the following trends. Once again, the upper plot here represents the output CO2 from the vent measured directly by the Lycor located at the vent's outlet. The bottom plot represents the concentration of CO2 in the air at the detection tower located some distance away from the vent. Looking at this period of time, we can see that although the vent's output is fluctuating, it remains well above the 395 or so part per million ambient concentration of CO2. This indicates that we should be able to detect this large source of CO2 from our detection tower. However, if we look at this graph, we can see that we're only detecting an elevated signal of CO2 periodically, and that sometimes we are not detecting any elevated level of CO2 at all. Let's examine the air movement patterns during periods of both detection and non-detection. A helpful visual aid in looking at these signals is a wind-rose diagram, which uses wind speed and direction as measured by the 3D anemometer to plot a frequency diagram with different bins representing different directions of wind. Recalling that the detection tower is located due east of the vent, let's take a look at the wind-rose diagrams during periods of non-detection when levels of CO2 are relatively flat and near ambient. During each of these periods of non-detection, the wind-rose diagrams show us that winds are either predominantly coming from the east or are sporadic and variable, with winds coming from all directions. This indicates that air from the vent is not reaching the detection tower. Conversely, if we look at periods of time during which there is clearly an elevated signal of CO2, we see that nearly all of the wind is coming from the west as it blows the CO2-laden air towards our detection tower. This analysis indicates that we are in fact detecting the vent's emissions and that we can accurately predict the direction of the leak. The final hurdle to clear, and by far the most difficult, is to try to quantify as a mass flux in mass per time how much CO2 is leaking from a source, and to do so from a distance using our detection tower. How do we do this? Let's first zoom in and assess our ability to quantify the mass flux leaving the vent using volumetric concentration and velocity measurements taken directly at the vent exit. The task was to develop a procedure for using these measurements to calculate a mass flux exiting the vent. However, even if a procedure could be developed, how could we check the validity of our calculations? Building smaller scale versions of the vent on the Union roof allowed us to control as many variables as possible. The key in this decision was the realization that we could directly measure the mass flux entering a bench scale model by weighing a canister of CO2 and recording its change in mass over time. The vents were designed as follows. A CO2 canister was placed on the scale, detailed in the equipment section, capable of recording the weight of the canister at certain time intervals. Attached to the canister was a pressure regulator and a rotometer controlling the volume of flow into the system. A tube was run through the top or side of the vent and terminated in a diffusion device to ensure equal radial CO2 release. A fan at the bottom of the cylinder blew the CO2 infused air up and out of the vent annulus, just as occurs in the Union roof vent. This system allows for an accurate check of mass flux, as all loss of mass from the cylinder made its way into the vent. This mass flux was constant, as verified by the plot of mass versus time recorded by the scale. The r-squared value of 1 here indicates this perfect correlation, and the constant mass flux was equal to the slope of this line. Now that the mass flux entering the system was a known quantity, we set about developing a procedure for measuring the mass flux using concentration and velocity. By splitting the annulus into smaller sections, we were able to measure the concentration and velocity at each location and represent that specific section of the vent by a single measurement. The entirety of each experiment looks as follows. At each measurement position, the Kestrel 4000 anemometer and Picaro spectrometer measured the velocity and concentration for a set amount of time. When positions were changed, the measurement device was removed from the vent to set a break in the data for easy visual verification that the velocity and concentration data coincided in time. The positions were then split up, and the data seen here represents data collected for a single position during the experiment. The blue line depicts velocity, the red line represents the concentration of CO2 leaving the vent, while the green line shows the concentration of CO2 entering the vent, to be subtracted off the red concentration for a net vent CO2 level. Using the equation seen here, which is derived in detail in the bench scale experiment video, we are able to calculate a mass flux for each section. Assuming each section's mass flux is representative, we follow these equations to obtain our final result, a mass flux of CO2 in grams per second, which depends on the various measurements at each position of velocity, concentration, and temperature, as well as the area of the vent and other constant variables. The results of experiments using 3 different size vents are seen here. As we can see, at higher mass fluxes, we consistently underestimate the value as measured by the scale. The reasons for these underestimations are still being worked out. Speculation leads us to believe it may be a problem involving the underestimation of velocity or concentration, or both, a product of the poorly mixed nature of the higher mass flux systems, or a separate unknown issue. We then move our bench scale techniques to the roof to produce a mass flux depending on a single point concentration and velocity value. Because of the chaotic nature of the CO2 concentrations exiting the vent, 2 measurement points were deployed, one moving and one stationary. The stationary measurement device consisted of the Vantage Pro 2 anemometer clipped to the vent in conjunction with the Lycor 8100 spectrometer. The moving measurement device was again the Kestrel anemometer and Picaro spectrometer. The goal here was to develop a moving mass flux function leaving the vent as given by a single stationary velocity and concentration measurement. Data from these experiments are still being analyzed, but here are some preliminary results. Looking at the moving and stationary concentration measurements, we see that in general, the air coming from the vent is well mixed. If we zoom in on one particular location and shorten the time scale, this well-mixed characteristic becomes more apparent, as both the moving and stationary concentration values remain nearly equal no matter the position. Next, we look at the velocity measurement. Unlike the concentration measurements, velocity remains relatively constant with time, as shown by the purple stationary measurement, but varies with position, as shown by the moving black measurement. Mathematically, these concepts break down into the following. Concentration varies substantially with time, but does not vary with position. Conversely, velocity does not vary substantially in time, but does change with position. Using the equation for mass flux presented before, the following changes occur. Because concentration is constant with position, we can treat the concentration as equal for all positions and pull it out of the sum. This allows us to only need one measurement position for concentration. Also, because velocity does not vary in time, we can develop a function which relates the velocity at one position to the velocities of all other measurement positions. Here is that result. Finally, we can use the function developed on the previous page to estimate the mass flux leaving the vent at any time based solely on the concentrations and velocities measured at one position. The ramifications of this become clear if we look back at this now familiar graph. While before we were simply comparing the concentration of CO2 leaving the vent with that of the detection tower, we can now apply our function to the concentrations and velocities measured and convert these data into a mass flux over time. This allows us to begin to relate the variables collected at the detection tower to the amount of mass leaving the vent. This brings us to the following future goals. Over the course of the coming years, we plan to employ machine and supervised learning techniques to relate the mass flux leaving the vent to the concentration, velocity, and distance variables at the detection tower. Allowing a machine learning algorithm to tease out trends will hopefully allow us to accurately quantify the size of a source in mass flux from an unknown distance away using only concentration and velocity data. We also hope to utilize machine learning to develop an automated and more robust lag time correction to the 3D anemometer and concentration data, as the methods employed now require an operator to introduce a spike into the system. Additionally, preliminary plans are in place to utilize the developed algorithms to see if we can detect the vent from detection towers already residing on other campus buildings farther away. Furthermore, we plan to change our mass flux function from a discrete sum-based equation to a continuous integral-based equation. By measuring velocity data in more locations around the vent and by using a more accurate measurement device, we should be able to create a function for velocity as a continuous transformation of the velocity at one point and radial and polar coordinates. This creates a more accurate mass flux estimation and will improve the results of our quantification efforts. The final portion of this project consisted of developing a live stream of the detection tower data to be viewed and analyzed in real time. This is a general overview of how the live stream functions. Detailed explanations can be found in the stream video of this series. As we know, all begins with the Picaro and 3D anemometer collecting wind and carbon concentration data. Internally, the Picaro allows the user to specify a COM port to which to send the measured data. In this case, we send the data to a COM port featuring a connected XB transmitter. The XB operates on a Zigbee network and acts as a wireless serial cable. A receiver XB is connected to a Mac Mini server located nearby which has network capabilities. Just as a serial cable transmitting the measured Picaro data would deliver the data to the Mac Mini, so does the XB network. Running a cron shell script once a minute logs all of the data on the Mac Mini as they are received. The data are then sanitized using Python scripts to apply a time correction, eliminate bad lines of data, and format the data into an SQL-friendly format. The shell script then pushes the sanitized data into two SQL tables, one with the CO2 data and one with the anemometer data. The SQL tables are the holding place for the data to be worked on using R. The raw data are also backed up in multiple locations, but the true working data resides in the SQL database. Next, a continuously running R session, which can be located on any server with internet access, connects to the applicable SQL tables and draws new data according to a user-specified buffer time into the R session. More sanitizing code is run to rid the data of any spikes or empty lines which may cause plotting issues. Finally, using the shinyapps.io interface, a web-accessible app is deployed. The app updates the graphs at a user-specified interval, and the plots generated are shown within 1 minute of data collection. Here is the live stream in action. This R session is running the code necessary to publish the app to an online dashboard as seen here. Once again, the user can input a buffer size to specify how far back in time the plot should go. As new data is fed into the system, the plots are automatically regenerated and updated as a product of the R code. Additionally, we can do the same types of analyses carried out earlier in the video on the live data. Here we can see that during a period of non-detection, winds are predominantly out of the east, whereas if we look at the windrows diagram during a period of elevated signal, the windrows diagram points almost directly toward our source. This concludes the project overview video. Please be sure to check out the rest of the videos in the series and contact me with any questions you may have. Now, if you'll excuse me,